Simple log analysis. Various tools can take these log files and produce pretty reports about your website traffic. But for the sake of exercise, let's build our own, using basic Unix tools. For example, say you want to find the 5 most popular pages on your website. You can do this in a Unix shell as follows: :I. Read the log file. Split each line into fields by whitespace, and output only the 7th such field from each line, which happens to be the requested URL. In our example line, this request URL is /cnss/typography.cnss. Alphabetically sort the list of requested URLs. If some URL has been requested n times, then after sorting, the file contains the same URL repeated n times in a row. The unique command filters out repeated lines in its input by checking whether 2 adjacent lines are the same. The C option tells it to also output a counter. For every distinct URL, it reports how many times that URL appeared in the input. The second sort sorts by the number n at the start of each line, which is the number of times the URL was requested. It then returns the results in reverse R order, i.e. with the largest number first. Finally, head outputs just the first 5 lines n5 of input, and discards the rest. The output of that series of commands looks something like this: 4189/favicon.ico 3631/2013/05/24/ improving security of SSH private keys.html 2124/2012/12/05/ schema evolution in ever protocol buffers thrift.html 1339/915/css/typography.css. Although the preceding command line likely looks a bit obscure, if you're unfamiliar with Unix tools, it is incredibly powerful. It will process gigabytes of log files in a matter of seconds, and you can easily modify the analysis to suit your needs. For example, if you want to omit CSS files from the report, change the awk argument to $7!/.css$print$7. If you want to count top client IP addresses instead of top pages, change the awk argument to print $1, and so on. We don't have space in this book to explore Unix tools in detail, but they are very much worth learning about. Surprisingly, many data analyses can be done in a few minutes using some combination of awk, sed, grep, sort, unique, and zargs, and they perform surprisingly well. Instead of the chain of Unix commands, you could write a simple program to do the same thing. For example, in Ruby, it might look something like this. Counts is a hash table that keeps a counter for the number of times we've seen each URL. A counter is 0 by default. From each line of the log, we take the URL to be the 7th whitespace separated field. The array index here is 6 because Ruby's arrays are 0 indexed. Increment the counter for the URL in the current line of the log. Sort the hash table contents by counter value descending, and take the top 5 entries. This program is not as concise as the chain of Unix pipes, but it's fairly readable, and which of the two you prefer is partly a matter of taste. However, besides the superficial syntactic differences between the two, there is a big difference in the execution flow, which becomes apparent if you run this analysis on a large file. Sorting versus in-memory aggregation. The Ruby script keeps an in-memory hash table of URLs, where each URL is mapped to the number of times it has been seen. The Unix pipeline example does not have such a hash table, but instead relies on sorting a list of URLs in which multiple occurrences of the same URL are simply repeated. Which approach is better? It depends how many different URLs you have. For most small to mid-sized websites, you can probably fit all distinct URLs and a counter for each URL in, say, 1 GB of memory. In this example, the working set of the job, the amount of memory to which the job needs random access, depends only on the number of distinct URLs. If there are a million log entries for a single URL, the space required in the hash table is still just 1 URL plus the size of the counter. If this working set is small enough, an in-memory hash table works fine even on a laptop. On the other hand, if the job's working set is larger than the available memory, the sorting approach has the advantage that it can make efficient use of disks. It's the same principle as we discussed in SS tables and LSM trees on page 76. Chunks of data can be sorted in memory and written out to disk as segment files, and then multiple sorted segments can be merged into a larger sorted file. MergeSort has sequential access patterns that perform well on disks. Remember that optimizing for sequential I/O was a recurring theme in Chapter 3. The same pattern reappears here. The sort utility in GNU Core Utils Linux automatically handles larger than memory datasets, by spilling to disk, and automatically parallelizes sorting across multiple CPU cores. This means that the simple chain of Unix commands we saw earlier easily scales to large datasets without running out of memory. The bottleneck is likely to be the rate at which the input file can be read from disk. The Unix philosophy. It's no coincidence that we were able to analyze a log file quite easily using a chain of commands like in the previous example. This was in fact one of the key design ideas of Unix, and it remains astonishingly relevant today. Let's look at it in some more depth so that we can borrow some ideas from Unix. Doug McIlroy, the inventor of Unix pipes, first described them like this in 1964. We should have some ways of connecting programs like a garden hose screw in another segment when it becomes necessary to massage data in another way. This is the way of I/O also. The plumbing analogy stuck, and the idea of connecting programs with pipes became part of what is now known as the Unix philosophy, a set of design principles that became popular among the developers and users of Unix. The philosophy was described in 1978 as follows: make each program do one thing well. To do a new job, build afresh rather than complicate old programs by adding new features. Expect the output of every program to become the input to another, as yet unknown, program. Don't clutter output with extraneous information. Avoid stringently columnar or binary input formats. Don't insist on interactive input. Design and build software, even operating systems, to be tried early, ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild them. Use tools in preference to unskilled help to lighten a programming task, even if you have to detour to build the tools and expect to throw some of them out after you've finished using them. This approach, automation, rapid prototyping, incremental iteration, being friendly to experimentation, and breaking down large projects into manageable chunks, sounds remarkably like the Agile and DevOps movements of today. Surprisingly, little has changed in 4 decades. Another example of a uniform interface is URLs and HTTP. The foundations of the web. A URL identifies a particular thing resource on a website, and you can link to any URL from any other website. A user with a web browser can thus seamlessly jump between websites by following links, even though the servers may be operated by entirely unrelated organizations. This principle seems obvious today, but it was a key insight in making the web the success that it is today. Prior systems were not so uniform. For example, in the era of bulletin board systems, BBSS, each system had its own phone number and baud rate configuration. A reference from one BBS to another would have to be in the form of a phone number and modem settings. The user would have to hang up, dial the other BBS, and then manually find the information they were looking for. It wasn't possible to link directly to some piece of content inside another BBS. The sort tool is a great example of a program that does one thing well. It is arguably a better sorting implementation than most programming languages have in their standard libraries, which do not spill to disk and do not use multiple threads, even when that would be beneficial. And yet, sort is barely useful in isolation. It only becomes powerful in combination with the other Unix tools, such as Unic. A Unix shell like Bash lets us easily compose these small programs into surprisingly powerful data processing jobs. Even though many of these programs are written by different groups of people, they can be joined together in flexible ways. What does Unix do to enable this composability? If you expect the output of one program to become the input to another program, that means those programs must use the same data format, in other words, a compatible interface. If you want to be able to connect any program's output to any program's input, that means that all programs must use the same input/output interface. In Unix, that interface is a file, or, more precisely, a file descriptor. A file is just an ordered sequence of bytes. Because that is such a simple interface, many different things can be represented using the same interface. An actual file in the file system, a communication channel to another process Unix socket, stdin, stdout, a device driver, say /dev/audio or /dev/lp0, a socket representing a TCP connection, and so on. It's easy to take this for granted, but it's actually quite remarkable that these very different things can share a uniform interface, so they can easily be plugged together. Roman 2 by convention, many but not all Unix programs treat the sequence of bytes as ASCII text. Our log analysis example used this fact. Awk, sort, unic, and head all treat their input file as a list of records separated by the \n uline. ASCII 0x0 a character. The choice of \n is arbitrary, arguably, The ASCII record separator 0x1e would have been a better choice, since it's intended for this purpose, but in any case, the fact that all these programs have standardized on using the same record separator allows them to interoperate. The parsing of each record, i.e. a line of input, is more vague. Unix tools commonly split a line into fields by whitespace or tab characters, but CSV, separated, pipe separated, and other encodings are also used. Even a fairly simple tool like Zargs has half a dozen command line options for specifying how its input should be parsed. The uniform interface of ASCII text mostly works, but it's not exactly beautiful. Our log analysis example used print $7 to extract the URL, which is not very readable. In an ideal world, this could have perhaps been print $request URL or something of that sort. We will return to this idea later. Although it's not perfect, even decades later, the uniform interface of Unix is still something remarkable. Not many pieces of software interoperate and compose as well as Unix tools do. You can't easily pipe the contents of your email account and your online shopping history through a custom analysis tool into a spreadsheet and post the results to a social network or a wiki. Today it's an exception, not the norm, to have programs that work together as smoothly as Unix tools do. Even databases with the same data model often don't make it easy to get data out of one and into the other. This lack of integration leads to balkanization of data. Another characteristic feature of Unix tools is their use of standard input stdin and standard output stdout. If you run a program and don't specify anything else, stdin comes from the keyboard and stdout goes to the screen. However, you can also take input from a file and slash or redirect output to a file. Pipes let you attach the stdout of one process to the stdin of another process with a small in-memory buffer, and without writing the entire intermediate data stream to disk. A program can still read and write files directly if it needs to, but the Unix approach works best if a program doesn't worry about particular file paths and simply uses stdin and stdout. This allows a shell user to wire up the input and output in whatever way they want. The program doesn't know or care where the input is coming from and where the output is going to. One could say this is a form of loose coupling, late binding, or inversion of control. Separating the input/output wiring from the program logic makes it easier to compose small tools into bigger systems. You can even write your own programs and combine them with the tools provided by the operating system. Your program just needs to read input from stdin and write output to stdout, and it can participate in data processing pipelines. In the log analysis example, you could write a tool that translates user agent strings into more sensible browser identifiers, or a tool that translates IP addresses into country codes, and simply plug it into the pipeline. The sort program doesn't care whether it's communicating with another part of the operating system or with a program written by you, except by using a separate tool, such as netcat or curl. Unix started out trying to represent everything as files, but the BSD sockets API deviated from that convention. The research operating systems Plan 9 and Inferno are more consistent in their use of files. They represent a TCP connection as a file in /net/TCP. However, there are limits to what you can do with stdin and stdout. Programs that need multiple inputs or outputs are possible but tricky. You can't pipe a program's output into a network connection. Roman 3 if a program directly opens files for reading and writing, or starts another program as a subprocess, or opens a network connection, then that I/O is wired up by the program itself. It can still be configurable through command line options, for example, but the flexibility of wiring up inputs and outputs in a shell is reduced. Part of what makes Unix tools so successful is that they make it quite easy to see what is going on. The input files to Unix commands are normally treated as immutable. This means you can run the commands as often as you want, trying various command line options without damaging the input files. You can end the pipeline at any point, pipe the output into less, and look at it to see if it has the expected form. This ability to inspect is great for debugging. You can write the output of one pipeline stage to a file and use that file as input to the next stage. This allows you to restart the later stage without rerunning the entire pipeline. Thus, even though Unix tools are quite blunt, simple tools compared to a query optimizer of a relational database, they remain amazingly useful, especially for experimentation. However, the biggest limitation of Unix tools is that they run only on a single machine, and that's where tools like Hadoop come in.